What I'm going to try to do is explain why economists, in particular macroeconomists like myself and my friends, are interested and excited by Julia. It's my purpose. So here's the deal. So I'm going to tell you how I think about, or how modern macroeconomists think about macroeconomics and the economy. And so here goes. So first I'm going to tell you what a dynamic economic model consists of. The question is, what are the fundamental objects in play on the table? So there's going to be people. Now I'm going to convince you that I have a peculiar idea of what a person is in a minute. So what these people have is they have purposes, they have beliefs, and they have constraints. Okay, then there's going to be governments. Actually, they're going to be people or collections of people too. And they're going to have powers to tax, to spend, to borrow, and to redistribute in this little artificial mathematical world we're going to invent. Then there's going to be technologies. And what those are, they're methods for producing goods, services, and physical and human capital, for transforming one kind of object into another. That's what a technology is for us. So every time I say an object, it's going to be a function or a sequence. Okay, then the next thing is they're going to be stochastic processes. That's a probability distribution over a sequence. And they're going to describe information flows and economic shocks, like the one that may or may not have occurred last night. Okay. And then there's going to be an equilibrium concept. And that's going to describe how markets and rules and regulations reconcile different people's diverse purposes and possibilities. So our equilibrium concept is going to accommodate, constant change and surprises. It's not going to be a system at rest in that sense. Okay. Okay, so what are the purposes of quantitative economics? Why are we doing this? It's to interpret historical data in ways that distinguish cause from coincidence. That's worthwhile in itself, but the reason we like to do it is to doing that is a prerequisite to evaluating the consequences of alternative government policies. What difference does it make if you, our vision is going to be country like Australia and country like Argentina, basically the same thing, consists of a bunch of people, a bunch of resources, and they've had very different economic policies in the last 100 years with very different outcomes. We want a machine for understanding that. Okay, so this is going to be the tool that we're going to use. Some mathematicians recently gave this to these people aren't economists. It's going to be mathematical programming with equilibrium constraints. If you Google it, it's called MPEC. So here's a definition. So mathematical program with an equilibrium constraint, it's a constrained optimization problem in which the constraints include variational inequalities and complementary slackness conditions. So those variational inequalities or complementary slackness conditions, I'm referring to Kuhn-Tucker, they're describing the behavior, optimizing behavior of other people than the person that's solving this constrained optimization problem. So an example of this, there's going to be a government or a principal. The MIT micro guys would say they talk about principal agent problems. There'd be a government or a principal. It wants to maximize social welfare or some other objective. But it's not just facing nature, it's facing people. So among the constraints that the principal faces are private agents or other people's first order necessary, hopefully, and sufficient conditions for extremizing, maximizing, or minimizing their objectives. So there's a mathematical program with equilibrium constraints is a multi-agent problem. Okay. So there's an ancient Chinese proverb. The government has strategies and the people have counter strategies. That's 3,000 years old. So I'll tell you what the author of that meant by a strategy. A strategy is a sequence of functions mapping a history at time t into an action at time t. You got a problem with that? Okay, so if you play football or soccer or baseball, that's a strategy. Okay, and so there's interrelated strategies. Okay, so here's the deal. It's a great day to do this because of Brexit. People have incentives to forecast. Why? And actually, I went to a couple talks at this conference where they were using predictive control. It's exactly this. People's decisions at time t about what to do now depend on, in economics, prices and other people's decisions in the future. Why is the stock market reacting to don't look right now, to what it's not what happened yesterday, it's what the consequences for the future are going to be. Okay. So people's beliefs about the future affect their present decisions. That's the key thing. Okay. So modeling beliefs. Now here's a choice. Okay, and this is going to be ruthless. It's going to be ruthless and wrong and scientifically very useful. Just like a lot of things that physicists have done. So the key scientific choice is, how do you model people's beliefs about the future? How do their beliefs relate to the actual distribution of future outcomes? So what I have in mind, so here's the way I think about it. What's a model? So what I'm going to say is a model is a probability distribution over a sequence. That is a stochastic process indexed by some free parameters. That's what I mean by model when I say a model. So here, if you have a setting in which the people you are modeling or the objects you are modeling have to forecast the future, they have to have models because they're using models. What's a model? It's a probability distribution over a sequence indexed by some free parameters. How are they going to forecast the future? They're going to have some model. So inside of our models are going to be people with models. And then there's also nature or God, depending on your theology. And that's the truth, that's the real model. Okay, so what do? So we're going to use something called rational expectations. And this is going to be a heroic and very useful thing. And and I just read this book by Steven Weinberg, a physicist, called Explaining the World. And he has things like this all the way. This is going to be an assumption that's going to be a ruthless, useful modeling assumption. Okay, so here's the rational expectations assumption. It's communism. There's a common model that's possessed by everybody inside the model, by God, and by the model builder. There's one model. And what's a model? Probability distribution model. So there's one model. So the rational expectations model is those three all coincide. Everybody inside the model has the same probability distribution. They may have different information, so they condition down on different things. Okay. So that, what I just told you, that communism of models, where a model is probably the same thing, that's used throughout game theory, and it's used throughout macroeconomics and all practical economics, and it's a dimension reduction. So you see that. So if I have a model with, say I want to model a wealth distribution, and I have many different kinds of agents, and they're all in the business of forecasting the future, do I want to endow each one of them with their own model? And I pick up, think of how many parameters I pick up. That's a dimension expansion. So this is all just a ruthless dimension. And you know, Abraham Lincoln, so you could rationalize this in various ways. I like to rationalize it that way. Abraham Lincoln said, you can fool all the people all the time. You know, you can't fool all the people all the time. With that, okay. So here's rational expectations. So here's what I said. The people inside the model themselves have models. So they're solving predictive control problems. So there's a communism of models, and those are shared by nature, people inside the model, and the statistician. And what that does is gives you a lot of power to test the model. Because like we write down likelihood functions, we do generalized method of moments, and we use laws of large numbers, and when we use E, a mathematical object, is equal to 1 over t times a sum, we're ruthlessly using that. Okay, so why rational expectations? Robert Lucas, a great economist of Chicago, said, beware of theorists bearing free parameters. And you know, Bayesians say that all the time, and for a reason. Okay, so so the way this surfaces, and you can so dimension reduction. Many of the things I'm talking about have been touched on in earlier talks that I've heard, in terms of the objects in play and in terms of the scientific concerns about dimension reduction. I mean, that's what machine learning is. Okay, so for us, there's a self-referential aspect that the agent's beliefs about the future are actually influencing future outcomes. There's this loop. So there's a fixed point. So a rational expectations equilibrium for us, it's a probability distribution that satisfies a certain fixed point, and it's a mapping from a whole collection of perceived laws of motion to actual laws of motion. So what you and I think about and everything about is going to happen in the future. That's going to influence what we're going to do today. It's going to influence what the future is. So there's this big mapping. And what we're going to go for is a fixed point. Okay, so I talk about this communism of beliefs because my friends at Chicago don't like that. But it's not the same kind of communism that Lenin was into. Maybe in a way it was. Maybe in a way it is. But for different motives. So, okay, so that's it. So times arrows. So this is how, I've been to conferences with physicists, friends. This is something where economics and physicists, we use lots of the same mathematics, but there's some stuff going on in economics that's not in physics. So given the past, the present and the future are simultaneously determined. The arrow of time doesn't just go that way, it goes this way. Beliefs about the future, what people think about stock prices or interest rates tomorrow, is going to affect what they really are today. So, so what this does is, throughout economics, it brings out the importance of details of timing protocols in both theory and practice. Okay. I got to put that up again. It's the same thing. I'm going to put this up a whole bunch of times because it's, in a way, it's not new. All that's new is formalizing it. Okay, so I'm going to skip over this, but there's, you know, in terms of the financial crisis, there's two polar models of the financial crisis. And if there's questions, I'll have to. And what these models, they make different assumptions. One's a model of bank runs, and it's what this model motivated much of what Ben Bernanke did. It's a model of multiple equilibria. And then there's a distinct model of moral hazard. It's about adverse incentive effects of bailing out banks. And these polar models are the only two serious models, scientific models, of financial crisis. Financial crisis, economists and experts on finance don't say that the financial crisis happened because people are stupid. That's not their model. What they say is people were very smart, and they had rational expectations. But nevertheless, the way the system's put together, it was vulnerable to the financial crisis. And the scientific tool for understanding the financial crisis is to pursue that. So if you read, I don't recommend this, if you read various, the press, they'll have all sorts of stuff about greed and stupidity of economists and stupidity of traders caused the financial crisis. That work has contributed nothing to understanding the financial crisis, but this has. They're serious issues. So those use rational expectations extensively. I just want to mention that. So if there's time, I'll come back and talk about bank runs. But I actually want to leave time for Erica, who's going to do some real work. Okay. So I could tell you about bank runs and moral hazard. They're worth studying. And it's not easy to choose between them. By the way, President Franklin Roosevelt, who signed the deposit insurance law, he knew this. He took a lot of economics classes at Harvard, even though he made fun of what he learned there. He actually did learn a bunch of stuff. And he was opposed to deposit insurance because he understood moral hazard, and he was using a rational expectations argument. Okay. So now I'm going to tell you what the tools we have. And I'm getting close to why we like Julia, or why we're very excited about Julia, is because our models are going to be complicated in a sense I'm going to tell you about, and they're going to have a. We want to do some things with the models that I told you about, because we want to use them to understand causal structures, and then we want to use them to give policy advice in a serious way. And the way we're going to use them is we're not going to have I belong to the Chicago school and you belong to the Cambridge school. That's not our line. It takes a model to beat a model. And what's a model? It's a probability distribution over a sequence indexed by some parameters that you've estimated more or less precisely. That's our line. And that's the line of young people. Okay, so here's our key tool. It's going to be a joint density. I'll index it by T, or it's actually a sequence of densities, the way I've written it, over those Y's. Those Y's are outcomes, and thetas are my parameters. And those parameters what are they going to describe? They're going to describe things about preferences, technologies, all those objects I talked about earlier. That's what I mean. And that's an immense object. That sequence of densities. So now, I went to I sat at the conference where there were a bunch of physicists and chemists, and I learned this language. It's exactly what we do. Their object in play was that thing, except for them it was some star exploding or something like that. Okay, so they had that, and then they talked about two things. They talked about a direct problem and an inverse problem. I love that language. So what's a direct problem? Well, you fix theta, and then you figure out what the joint density is. You simulate it. So that joint density might be very hard to deduce and write down, and might take a lot of time. Julia. Okay. What's the inverse problem? You observe the Y's. You observe one realization of the Y's, and you invoke faith and God and laws of large numbers and central limit theorems and stuff like that. And you want to infer the parameters. So there I flip it around, and I want to back out theta from the observations. So there we use likelihood-based methods or Bayesian methods. They're both maximum likelihood. We use likelihood-based methods, maximum likelihood or Bayesian. Or we do something like there's guys at MIT in statistics and economics who do pseudo-Bayesian. So those are guys who, you come in and you say, I'm not a Bayesian. They say, oh, okay, I agree with that. What are you doing? You say what you're doing. They figure out that you were really a Bayesian. They back out. And that's been very fruitful. And so the revolution in computational Bayesian, you guys don't, so when I was your age, people said, Bayesian analysis, that's nice, you can never do it. Because you could not compute posteriors. except in very special, uninteresting cases. And because of computers, you now can. And so the computers, the ability to computational speed, completely changed. It completely changed people from being frequentists to Bayesian. It's a remarkable thing. And it came from computers. Not from computers, not from high-style computer scientists, but guys who are doing stuff like making stuff faster. So, okay. So what are the key tools that we use to do quantitative macroeconomics? We use Markov processes. And they're finding the state is an art. The whole deal there is lots of stuff you didn't think was Markov is Markov. So like a thing, we were talking to some people yesterday. So, one of the great people at MIT was Norbert Wiener, and he was interested in solving linear prediction problems, multivariate linear prediction problems. And he worked in the frequency domain in the space of infinite sequences, not Markov. And there were problems he worked on, couldn't solve, like factoring a multivariate spectral density matrix. Okay, so there's a kid named Kalman, who's an MIT graduate student, and finding the state is an art. He figured out how to write down basically a hidden Markov model that completely cracked a whole class of problems. And that opened up.
Can I tell everybody that Norbert Wiener's desk is still in the math department and it has a little plaque on it? Somebody's using it?
Yeah. I would actually like to see that.
I'll take you there lunchtime.
That's great. Okay, so actually figuring out how to solve, figuring out how to make problems Markov, was a big triumph of mid-20th century applied mathematics. So there's two things. There's sequential inference and optimization, and that has an interesting history. Abraham Wald invented the sequential probability ratio test, and Richard Bellman invented dynamic programming. And actually, if you go to Quanticon, there's a lecture about how Abraham Wald discovered that. And there's a notebook. And here's how he discovered it. Someone gave him the problem. And who gave him the problem? One of the most brilliant economists ever, Milton Friedman. And a Navy captain walked into, Milton Friedman was working in a statistical research office of the military during World War II, and a Navy captain came up and told him, I have a strategy, a decision rule that the Navy told me to use, and I think it's stupid. Why is it stupid? Because I think there's a better one. Here's a better one. And he said, I can't, why is it better, and why is that one stupid? Milton Friedman worked on this problem, couldn't solve it. Gave it to a couple statisticians, they couldn't solve it. Gave it to Abraham Wald, he solved it. And he wrote this book called Sequential Analysis, and it's a beautiful book. Read it today, it's very exciting. And then dynamic programming is invented by Richard Bellman. Actually should have Kalman. So filtering, smoothing problems were solved by Kalman, and now today it's nonlinear filtering, which are basically versions of hidden Markov models. So those are our tools. They're everybody's tools. So now I'm going to show you a Bellman equation. Okay, and so we use this over and over again. You may recognize it as in continuous time. It's a Hamilton-Jacobi-Bellman equation, and what it is, it's a consequence of a huge bluff. It's a bluff, and what I mean by that is you have this complicated dynamic optimization problem, which is an infinite time, infinite horizon. And what you say at the beginning of this is, let V of x be the answer to the problem. You pretend like you know what the answer is. In particular, what V of x is the optimum value starting from state x. And you just say, suppose I knew that. Which, of course, the whole deal is to find it. So you don't know it. So you pretend like you know it. That's the bluff. And so you do it. So if you know it, V of x, the value function, has to satisfy that functional equation. It's and there it is. Your one-period utility function is u of the state today and some action you take, c, and then beta is a discount factor, and then tomorrow the state's going to be X star, but you don't know X star. It's governed by some probability distribution. It's a conditional distribution that's partly determined by what you do. So there it is. There's V on the left and there's V on the right. So you didn't know it to begin with, and you don't know it now. But you know it has to satisfy that so-called principle of optimality. Well, that's a functional equation. And okay, in general, it's easy to write that down. It's hard to solve it, especially if X has high dimension. That's where we need Julia. So that's a Bellman equation. It's called dynamic programming. That's called dynamic programming. That's the functional equation of dynamic programming. And then you've seen, I saw some yesterday, Hamilton-Jacobi-Bellman equations. They're continuous time versions of that. If you stare at that, you'll see it's really, so how do you solve that? So if you're a Julia guy, how do you solve that? Well, people have devoted, okay, so this is going on in Julia. There's various clever ways. The simplest way is iterate. Make a guess at the thing on this side, compute the thing on this side, then do it again. And what you can prove is, actually a great mathematician, David Blackwell, proved that that's a contraction. So it's guaranteed, has very good, nice convergence properties. Slow, but it's going to start from anywhere. Practically, if you look at that, that's naturally, trivially parallelizable. Because what you do is, at each x, you've got to solve a distinct max problem. So you can farm those out. But there's the curse of dimensionality. So one frontier, and this is where Julia, bread and butter for us. Okay, so now I'm going to show you, so that's a so-called single agent problem. So that's 1970s, 1980s breakthrough in macro and micro and game theory. Okay, so now I'm going to show you to the 2000s breakthrough. It's going to be dynamic programming squared. So what's dynamic programming squared? Okay, so look at that Bellman equation. So there, X is a state. So finding the state is an art. So X is just a state, and you could see what it is. It's just governed by that controlled Markov process. What's dynamic programming squared? And for financial crises, we want to solve dynamic programming squared problems. So what these things are, they have Bellman equations inside the Bellman equation. So I know what you're thinking. I'm going to get famous by having a Bellman equation cubed. And actually, I went to a lecture about, it blew me away, metaprogramming. Okay, but don't do that, because I'm going to do that. Okay, so what these have, Bellman equations inside Bellman equations. Okay, so what is the Bellman equation? So it's a value function. One of the states in the Bellman equation is the value function for somebody else. And this gets back to the, okay, so I'm going to write one down. So those inner Bellman equations describe the responses of people whose incentives are affected by government policies. Like the guys who wrote Dodd-Frank wish they'd had this. They're making guesses. Okay, so I'm almost going to stop here. So here's a dynamic programming squared problem. So here's the deal. I just write down that Bellman equation. Okay, so there it looks. It's got some stuff it's got some stuff today, and it's got beta times some stuff tomorrow. But now I added a decision variable. There's a D, a C, and now part of the decision variable is to choose something called V of X star. That's your value function for next period. But you're solving that problem. I'm not solving it. But now this is a mathematical program with equilibrium constraints. So look at the maximization now. It's subject to your Bellman equation. Okay, so let's say I want you to be the government, and I'm just the guy. So that's my Bellman equation, that V of X, just in the natural state. And I do that. Of course, I have to take account of D because D is influencing stuff, and D is chosen by the government. Like, I won't scare the hell out of you, but Trump's, okay. Trump's. Okay, that's D. It might be. If you think it can happen here, where are you from? Okay, so it can happen. So anyway, so that's it. So D's in there. So now I've got my Bellman equation, and that's in there because why is D in there? The ancient Chinese proverb. That's why D is in there. So I'm taking that into account. Now you're the government. I'm just not going to give names because I've got myself upset already by that. Okay, so now what the government's doing is, look what it's doing. It's solving a Bellman equation. It's got some R, X, and D. That R could actually be, it could be a benevolent government, same. Okay, but it's got that. And then what's it choosing? It's manipulating my continuation value function, knowing my value function today. Okay, so this was invented, this stuff has emerged gradually. This is a very powerful tool. And if you want to learn about it, I can show you some QuantiCon lectures, which are going to, and Julia and it's a great tool for doing this because these are nasty. It's easy to write down, but actually figuring out how to solve it, that takes some, it takes some creativity. And actually, in economics, the guys who've, in my opinion, the guys who deserve a lot of credit aren't just the guys who wrote it down. They're the guys who figured out how actually to put this on a computer. And the way I see things going is, I heard a talk from the Moore Foundation yesterday that deserves a lot more credit, and it's up to us to make sure it gets credit. Okay, so that's that. So that one slide, that's one of the frontiers, and it is a Julia advertisement. It's a walk-in advertisement for Julia and things like Julia. Or, maybe some young kid is sitting here and he is saying just Julia stuff. To me, that just looks like MATLAB did, and I know a way to make that those 1600 factor 1600 speed gains. That's nothing, So hopefully there is somebody like that. So. Guys like me and are going to benefit from that. So here's the deal. Dynamic programming squared, some of the constraints are forward-looking. So if you look at that constraint, you show that to a physicist and say, wait a minute, the law of motion has to go backward. No, the arrow time's going forward. So look at that. But a mathematician doesn't care whether it's going backward or forward, even if a physicist does. So some of these constraints are forward-looking, and again, the arrow of time reflects people's incentives to forecast future actions of their competitors and regulators. The persistent challenges, the curse of dimensionality, and we have to repeatedly solve large numbers of simultaneous inequalities. Not just equations, inequalities. So they have, which we convert to equalities in order to fit the model to data. So I'll conclude by saying that. And now I'm eager to hear the next talk because it's going to be payoff.